Atoms are the building blocks of the universe. They make up everything you see around you. But what makes up an atom? At the very center of an atom is the nucleus, which is made up of small particles called protons and neutrons. Protons are very small, positively charged particles, and neutrons are neutral particles that have no charge. Atoms can have just one proton, or they can have multiple. A group of atoms that all have the exact same number of protons are called an element. For example, hydrogen is an element with one proton in the nucleus, and carbon is an element with 6 protons. In general, an atom will have a specific number of neutrons in the nucleus, meaning the atom won't lose or gain any neutrons for a very long time. This is called a stable atom. Usually, a stable atom has an equal number of neutrons and protons, but there are exceptions. To find the mass number of an element, you add the number of protons and neutrons together. So, protons plus neutrons equal mass number. This gives us names like carbon-12 or carbon-14, which are types of carbon atoms used in carbon dating. Orbiting the atom's positively charged center are particles with a negative charge called electrons. The electrons are attracted to the positive nucleus, but they can escape their orbit by an outside force. Atoms have a certain number of electrons orbiting the nucleus. If the number of electrons is equal to the number of protons, the overall electric charge of the atom is neutral. If that atom has more electrons than protons, its charge will be negative. With fewer electrons than protons, the atom will have a positive charge. The electrons determine how atoms interact with each other. Atoms can share electrons to form molecules, which are particles made up of many atoms. Water is made up of 2 hydrogen atoms and 1 oxygen atom. These 3 atoms share electrons. Now that we have talked about the different parts of the atom, let's summarize a few properties of atoms. Atoms have an atomic number, which is the number of protons in the nucleus. The periodic table arranges atoms in increasing atomic number. The charge of an atom is calculated based on the difference between the number of protons in the nucleus and the number of electrons orbiting the nucleus. Here's a quick review. An atom is made up of protons, electrons, and neutrons. The number of electrons will determine how atoms interact with one another and decide if the atom as a whole is positive, negative, or neutral. The mass number of an atom is found by adding together the number of protons and neutrons. And finally, the charge of an atom is determined by the number of protons and electrons in the atom.
Hi, and welcome to this video on the mole, the unit used to describe the amount of particles, atoms, and molecules in chemical reactions. Today, we'll cover more about what the mole is, where the concept came from, and how to use it in chemical calculations. To start, here's the very simplest explanation of what a mole is and what it's used for. A mole is a number that allows chemists to count atoms and molecules by using mass instead of counting them individually. Now, let's dig into this a bit. By definition, a mole is 6.022140076 times 10 to the 23rd units of something, which is usually reduced to 6.022 times 10 to the 23rd. It's a proportionality constant relating the number of units in a sample to the amount of a sample, which we can write out in this equivalency. 1 mole equals 6.022 times 10 to the 23rd units of something. As it turns out, this is a famous number, known as the Avogadro constant or Avogadro's number. This number is named after Amedeo Avogadro, an Italian scientist from the late 1700s, who first documented the relationship between the volume of a gas and number of gas particles. We can apply the concept of a mole to anything, not just molecules or atoms or anything else related to a chemical reaction. I could tell you that I have a mole of marshmallows, which would mean that I have 6.022 times 10 to the 23rd marshmallows. Now, obviously, this is a ridiculous number of marshmallows to have. Just look at the number written out. That's a lot of zeros. It's such a large number that our poor human minds have trouble comprehending it. Think about a mole of seconds, for example. That's about 600 sextillion seconds, which ends up being 2.73 times 10 to the 15th years. Some scientists believe that the Big Bang only happened 13.7 times 10 to the 9th years ago, so the universe isn't even a mole of seconds old. That's how large this number is. So why do we need such a ludicrously large number? Well, it turns out that when you're dealing with something as small as atoms, Avogadro's number isn't that large. 1 mole of carbon atoms would just be 12 grams of carbon. If that 12 grams seems oddly precise, that's because scientists specifically selected the value of the mole so that a substance in grams would be numerically equivalent to the average mass of 1 molecule of the compound in atomic mass units. Okay, let's unpack that for a second. We need to understand how Avogadro's number was originally calculated because, as you may have guessed, scientists didn't pick 6.022 times 10 to the 23rd for the way it rolls off the tongue. They picked it because it actually makes calculations easier and more intuitive. The atomic mass unit is defined as 1/12 of the mass of 1 carbon atom, which is 1.660 times 10 to the negative 27th kilogram, a very, very small number. Remember, a carbon atom has 6 protons and 6 neutrons, which make up the vast majority of the atom's weight. So an AMU is roughly the weight of a single proton or neutron. This was, in a way, by accident. At the time, scientists didn't even know that protons, neutrons, or electrons existed. They defined carbon as 12 because they wanted the lightest element, hydrogen, to be 1, which in a way does acknowledge the existence of subatomic particles, just not intentionally. Regardless, by definition, a carbon atom is 12 AMU. Because the AMU is such a tiny number and we rarely ever interact with one atom or molecule, scientists wanted a unit to describe larger amounts of material while maintaining the intuitiveness of the AMU. After all, it does make sense that carbon should weigh 12 AMU since it has 12 nucleons. The mole provides us with the very useful concept of molar mass, the mass in grams of 1 mole for any compound. And since scientists defined it this way, the molar mass is numerically equivalent to the AMUs in the chemical element or compound. In the case of carbon, the molar mass of carbon is 12.01 grams per mole. You might immediately be wondering, why isn't the molar mass of carbon exactly 12 grams per mole like we said earlier? That's because for the molar mass, we're taking into account the naturally occurring carbon isotopes that slightly adjust the total mass of a bulk carbon sample. So when we made that calculation earlier, we assumed that every single one of those 6.022 times 10 to the 23rd carbon atoms were carbon-12 atoms, when in fact, some of them were carbon-13 and carbon-14. So when we have a naturally occurring sample of carbon, say in a diamond, the weight in grams of 1 mole is best estimated as 12.01 grams per mole, which reflects the natural abundance of the different carbon isotopes. All right, now that we've established what the mole is and how it was originally calculated, let's turn to why it's so useful when dealing with chemical reactions. Consider the successful combustion of methane with oxygen. Say you have 100.0 grams of methane. How much oxygen do you need to react with it? To know that, we have to know about the chemistry of the reaction, which is done on a particle basis. What we mean by this is that we can't think about reaction chemistry in grams. We have to think about it in terms of the molecules reacting with each other. In other words, the number of methane molecules in 100 grams of methane is different than the number of oxygen molecules in 100 grams of oxygen. So we can't simply say that 100 grams of oxygen should react with 100 grams of methane because there are actually more molecules of methane in 100 grams than oxygen molecules in 100 grams of oxygen. If we look at the combustion of methane, you see we need 2 molecules of oxygen for every molecule of methane. On a large scale, we could say that we need 2 moles of oxygen for every mole of methane. Now, we need to figure out just how many moles of methane are in 100 grams. So using the molar mass of methane, 16.04 grams per mole of methane, we show that 100 grams of methane is 6.23 moles, which means we need 12.46 moles of oxygen to completely react with the methane. To sum up, the mole provides us with a unit to convert from the microscopic world, where there are billions upon billions of particles, to our macroscopic world, where we don't often deal with numbers that large or small. Scientists conveniently defined it so that the molar mass, the grams of 1 mole of substance, is relatively intuitive in that it is roughly numerically equivalent to the number of nucleons in the compound. All right, with that, let's wrap up with a couple of practice questions. If you'd like to work these out on your own, feel free to pause the video after I read the question. Number 1, if we estimate the world population at 8 billion people, what is the world population in moles? To convert the world population to moles, we use the following calculation to find that there are only 1.3 times 10 to the negative 14th moles of people on Earth. That's a really small number and makes the global population also seem small. But of course, we know that it's actually quite a lot of people. So while we can use moles to describe anything, it doesn't always make sense to use them. This is one of those cases. Number 2, this question is really 2 related questions. How many moles are in an 8-ounce cup of water? How many hydrogen atoms are there in the 8 ounces of pure water? To calculate the number of moles in 8 ounces of water, we need to convert ounces to milliliters, then to grams, which we can then convert to moles using the molar mass of water, which is approximately 18.02 grams per mole, which makes sense since oxygen has 16 nucleons and each hydrogen has 1, which makes 18. Then it's just simple multiplication. This shows that 8 ounces of water is 13.14 moles of water, which means that when you drink that cup of water, you put 7.9 times 10 to the 24th molecules of water into your body. Now, to calculate the number of hydrogen atoms in that cup of water, we simply need to multiply the number of moles by 6.022 times 10 to the 23rd, and then multiply by 2 since there are 2 hydrogen atoms for every mole of water. This gives us 1.58 times 10 to the 25th hydrogen atoms, which is a lot of atoms. Best to stick with moles for this.
Have you ever classified something based on what you observed about it? Perhaps you've distinguished a dog from a cat based on the dog's larger structure, flappy ears, and longer head shape. Maybe you've distinguished a chocolate lab from a golden retriever because the chocolate lab was brown, had shorter hair, and more compact hair. What we observe helps us to make distinctions. Being able to make observable distinctions is a very good and necessary tool in life. And this absolutely applies to the sciences. Now, properties are just characteristics of something. A physical property describes an observable change in a substance's characteristics, but does not affect the chemical makeup of that substance. Let's take a look at some examples of physical properties of matter. Boiling point. A substance's boiling point is a physical property. For instance, when water or H2O boils, so when it converts from a liquid to a gas or water to steam, it is still water. The chemical identity is still H2O. The chemical property hasn't changed, only its physical property has. So, if there is an observable change, but the chemical identity does not change, then you have a physical change. Melting point. Take ice, for example. When ice melts into liquid water, the chemical identity doesn't change. The identity of ice is still H2O. When ice melts, the only thing changing is its physical state. A physical property is anything you can hear, see, touch, smell, or measure and observe in some form without changing the chemical identity of the substance. Along with boiling point and melting point, this includes solubility. This is a substance's ability to dissolve in a solvent. It also includes pressure, color, shape, malleability, which is a substance's capacity to change form or deform under pressure, volume, This describes the amount of space occupied by a substance. Viscosity, the thickness or semi-fluidity of a substance because of its internal friction. Temperature. Electric charge, which is a property that causes matter to encounter force when inside of a magnetic field. Density, which describes how close or how far apart the atoms within a substance are. These, along with others, are all examples of physical properties of matter, but these do not change the chemical identity of the substance. Now, a chemical property, on the other hand, can only be observed after a chemical reaction has taken place. So after the chemical has gone through an identity change. This includes irregular change in color. If you mix white and red together and get pink or light red, then that's probably not a sign of a chemical reaction. That's just what happens when you mix the colors red and white together. However, if you mix a red and a white substance together and get blue, then you may have a chemical reaction. Change in consistency. When two substances are mixed together and there is a change in consistency, then this may reflect a change in the molecular structure. So if you take two runny liquids and mix them together and the product is a thick jelly substance, then you might have a chemical reaction. Change in luster. Luster refers to the reflective quality of a substance. So if you mix two dull, murky substances together and they produce a really glossy or polished substance, then you might have a chemical reaction. The formation of froth or bubbles may suggest that a gas has been composed in the chemical reaction. Change in odor. Now, if it's just a slight change in odor, it's probably not a chemical reaction. So if I mix a substance that smells like honey, this is just a silly example, but I mix it with a substance that smells like vanilla and the ending result smells like some type of syrup, then it's more than likely not a chemical reaction. If you take those same two substances together and their product smells like a smelly sock, then you may have a chemical reaction. Change in temperature. You can use a thermometer to take the temperature of each substance before, and if there is a change after the two have been combined, then there may be a chemical reaction. Precipitate formation. This just means that an insoluble solid is formed from a liquid solution. If this happens, then you probably are witnessing a chemical reaction. So, physical properties are observed without the substance undergoing a chemical identity makeover, and chemical properties are observed after chemical reactions have taken place.
Hello, and welcome to this Mometrics video on specific heat capacity, a constant that relates heat transfer to changes in temperature. Temperature is directly related to the average translational kinetic energy of the atoms or molecules in a system. Basically, the faster and heavier the particles are, the higher the temperature. The units for temperature are degrees Celsius and Kelvin. Remember, 0 degrees Celsius equals 273 Kelvin, but 1 degree Celsius has the same magnitude as 1 Kelvin. Conversely, heat is measured in joules and is the energy transferred between systems at different temperatures that are in contact. Because heat is the transfer of energy, it is known as a process quantity. When heat is absorbed or released by a system, the temperature changes. How much the temperature changes depends on the substance and specifically the specific heat capacity of that substance. Let's look at an example. Let's say we have 47.8 grams of water at 35 degrees Celsius and we put it on the stove. We turn on the stove and transfer 1,000 joules of heat to our water and the temperature rises to 40 degrees Celsius. In other words, it took 1,000 joules of heat to raise 47.8 grams of water by 5 degrees Celsius. That's kind of a mouthful and seems oddly specific in terms of quantities. This is where specific heat capacity, notated as C, comes into play. It's a standard quantity and is the amount of heat required to raise 1 gram of a substance by 1 degree Celsius. With some simple division, we can derive the specific heat capacity of water from our hypothetical cup of water. Specific heat capacity, C, equals heat released, Q, over mass times change in temperature, delta T, equals 1,000 joules over 47.8 grams times 5 Kelvin, which equals 4.184 joules per grams Kelvin. From this, we know now that it takes 4.184 joules to raise the temperature of 1 gram of water by 1 degree Celsius. That's the specific heat capacity of water. This is really helpful to scientists because once determined, the specific heat capacity can be used to calculate the heat absorbed or released by a system simply by measuring the temperature change and mass. Let's try that out. Let's look at a new cup of water. Let's say a mug of 350 grams that's boiling. The water starts at 100 degrees Celsius and cools down to 90 degrees. We want to know how much heat was released from the water to the surrounding environment. Since we know the specific heat capacity of water is 4.184 joules per gram Kelvin, we simply need to rearrange our previous equation to solve for Q, the heat released. Remember, heat energy is specific heat capacity times mass times change in temperature. In this example, that is 4.184 joules per gram Kelvin times 350 grams times negative 10 degrees Kelvin, which is negative 14,644 joules. Since we knew the specific heat capacity of water, calculating the heat released from the system was easy. Note here that the negative sign simply tells us that the system, the mug of water, released heat to the surrounding system rather than absorbed it. Now that we've defined specific heat capacity and demonstrated how it can be used to calculate the heat transferred from or to a system, let's look at why the specific heat capacity changes between substances. For example, the specific heat capacity of ethanol is 2.18 joules per gram Kelvin, almost half of water. If we have 1 gram of water and 1 gram of ethanol, both at 0 degrees Celsius, it would take 4.18 joules of heat to raise the temperature of water to 1 degree Celsius and only 2.18 joules for ethanol. The liquids reach the same temperature but require different amounts of heat. Why? Remember, to increase the temperature, we need to increase the average translational kinetic energy of the molecules, make the molecules move faster. But the internal energy of a substance is more than just the translational kinetic energy. It also includes potential energy from intermolecular interactions. When heat is transferred to a system, it is distributed amongst the kinetic and potential energies. So, if a system has more potential energy, a smaller proportion of the transferred heat is distributed to the kinetic energy, yielding a smaller increase in temperature. To better understand this concept, let's look at water and ethanol again. In water, there's a complex network of hydrogen bonds between the molecules. Those interactions are part of the potential energy and need to be overcome, or broken, to increase the average translational kinetic energy. So, when we heat water, some of that energy is used to break up the hydrogen bonding network instead of increasing the kinetic energy, resulting in a large specific heat capacity. Conversely, in ethanol, there are fewer hydrogen bonds per molecule, or less potential energy, and therefore a larger proportion of the heat transferred is used to increase the average kinetic energy, which results in a smaller specific heat capacity. Okay, let's wrap up with a review. First, we reviewed the scientific definitions of temperature and heat and related them using specific heat capacity. Using water as an example, we showed how once we know the specific heat capacity, it is quite easy to determine the heat transferred from or to a system. And finally, we considered from a microscopic view why substances have different specific heat capacities.
Hey guys, welcome to this Mometrics video over chemical reactions. In this video, we'll take a look at the definition of a chemical reaction, characteristics of chemical reactions, types of chemical reactions, and other things that are pretty important to know. First, the definition. A chemical reaction has taken place when a chemical substance alters its initial chemical identity and takes on a new chemical identity. So basically, what's happening is you have at least two molecules that come together perfectly, hitting each other in the exact right way, and these two molecules, change into something else. That's typically how all types of reactions work. For example, you have an eager and excited teacher who says, "Science is very important. You need to learn. So do your homework, do your homework, do your homework." Then let's add to the equation that one guy in the class who says, "I didn't do my homework." When these two come together and react, the product will be a very unhappy teacher and a slightly terrified young boy. In this example, we can see some observable differences after the reaction has occurred. Well, the same thing is true with chemical reactions. Every chemical reaction yields a different result, which inevitably means that chemical reactions will not all have identical observable properties. However, if you mix two chemicals together and want to know if they reacted with one another, you could look for these observable characteristics. Irregular change in color. If you mix white and red together and get pink or light red, that's probably not a sign of a chemical reaction. That's just what happens when you mix the colors red and white together. However, if you mix a red and white substance together and get blue, then you might have a chemical reaction. Change in consistency. When two substances are mixed together and there's a change in consistency, then this may reflect a change in the molecular structure. So if you take two runny liquids and mix them together and the product is a thick jelly substance, then you might have a chemical reaction. Change in luster. Luster refers to the reflective quality of a substance. So if you mix two dull, murky substances together and they produce a really glossy or polished substance, then you might have a chemical reaction. Appearance of bubbles or froth. The formation of froth or bubbles may suggest that a gas has been composed in the chemical reaction. Change in odor. Now, if it's just a slight change in odor, it's probably not a chemical reaction. So if I mix a substance that smells like honey, now this is just a silly example, with a substance that smells like vanilla and the ending result smells like some type of syrup, then it's more than likely not a chemical reaction. If you take those two same substances and mix them together and their product smells like a smelly sock, then you may have a chemical reaction. Change in temperature. You can use a thermometer to take the temperature of each substance before, and if there's a change after the two have been combined, then there may be a chemical reaction. Precipitate formation. This just means that an insoluble solid is formed from a liquid solution. If this happens, then you probably are witnessing a chemical reaction. So those are some observable characteristics that may signify that a chemical reaction has taken place. Now let's take a look at 5 different types of chemical reactions. Number 1, combination reaction or synthesis reaction. A combination reaction is pretty straightforward. It can be defined as when substances are mixed together and they form a new compound. Here's what the combination reaction equation looks like. A plus B yields AB. As you can see, these two substances literally combine to form a new substance. An example of this is carbon solid and oxygen gas reacting together to form carbon dioxide gas. Number 2, single replacement reaction. A single replacement reaction, also known as displacement reaction, can be defined as a chemical reaction in which one element displaces or replaces, whichever word you would like to use, a comparable element in the compound, causing a chemical change in the compound. Here's what that looks like in equation form. A and B plus C yield AC plus B. As you can see in this equation, C has stepped in and replaced or displaced B. An example of this is the combination of copper and silver nitrate. 3, double replacement reaction. A double replacement reaction can be defined as a chemical reaction in which the ions of two compounds swap with one another within a liquid solution and configure two new compounds. Here's what that looks like in equation form. An example of this is the combination of sodium sulfide and hydrogen chloride to produce sodium chloride and hydrogen sulfide. Sodium and hydrogen are cations, and sulfur and chlorine are anions. The cations and anions switch places during the reaction to form new compounds. Number 4, decomposition reaction. Decomposition and composition are opposites. In a decomposition reaction, a single complex compound is broken down or decomposed into a more basic substance. Here's what that looks like as an equation. AB yield A plus B. Now, there are actually 3 different subtypes of decomposition reactions: thermal decomposition, photodecomposition, and electrolytic decomposition. The term that precedes the word decomposition refers to the type of energy used to make the decomposition possible. So, in thermal decomposition, heat is added to the complex compound to decompose it. In photodecomposition, photons, or light, is added to the complex compound to decompose it. And in electrolytic decomposition, electric current passes through a liquid solution to decompose it. For example, the electrolysis of water. Water decomposes into hydrogen and oxygen when an electric current is added. Number 5, combustion reaction. A combustion reaction can be defined as a chemical reaction where a substance mixes with oxygen and produces substantial amounts of energy that take place in the form of heat and light. An example of this would be the combining of methane and oxygen to produce carbon dioxide and water. Now, the last thing we'll talk about, as promised, is other things that are pretty useful to know. There's a lot that I could go into here, but I just want to talk about 2 things. The first is basic language, and the second is reaction rates. Basic language. You should already know this, but here it is. The individual substances, before they are combined together to react, are called reactants or reagents. These reactants, once combined, yield a product or products. Secondly, reaction rates. Now, there's a lot that goes into this, but I'll give you the most basic idea of what this means. Chemical reactions are all over the place when it comes to speed or rate it takes for the reaction to occur. Some reactions happen instantaneously, and others take years and years. Well, reaction rates are dependent upon certain characteristics of the reactants. There are 2 variables in which the reaction rate is dependent on: the change in concentration of a substance and the time it takes for the change to be observed. Well, this rate of change can be altered via a catalyst, which speeds up the chemical reactions, or an inhibitor, which slows down chemical reactions. Understanding how chemical reactions work is important, but understanding the rate at which they take place is equally as important.
Hi, and welcome to this video on the electromagnetic spectrum. In this video, we'll discuss what the electromagnetic spectrum is and go over the properties of electromagnetic waves. You may have heard of the electromagnetic spectrum, but what exactly does that encompass, and why is it electromagnetic? The electromagnetic spectrum is what we call all of the forms of electromagnetic radiation that travel at the speed of light while in a vacuum. All of these forms of radiation contain varying amounts of energy. Though we use the term radiation, only the higher energy electromagnetic waves are dangerous because they're able to penetrate cells more easily. You may be familiar with the color spectrum of a rainbow. This is actually just a small part of the electromagnetic spectrum. If you take that rainbow of colors and expand it out past visible light on both ends, you'll eventually end up with the whole electromagnetic spectrum. The highest energy part of the spectrum consists of gamma rays, and as you go down in energy, you find X-rays and then ultraviolet light, which is the radiation that causes sunburns. Next up is visible light, which is just the range of the spectrum that human eyes are able to detect. Violet light has the highest energy, just below ultraviolet, and red light has the lowest energy. Beyond that are infrared, microwave, and radio waves with the lowest energy end of the spectrum. All of these types of radiation act as waves with a wavelength measured in meters and a frequency measured in units of hertz or cycles per second. The wavelength of a light wave is considered to be the distance from crest to crest or trough to trough, where the trough is the lowest part of the wave and the crest is the highest. The frequency can be thought of as the number of oscillations per second, or the number of crests or troughs that pass a certain point per second. In a vacuum, these waves all travel at the speed of light, c, which is roughly 300,000 kilometers per second, faster than anything else in the universe. However, when light is traveling through air, water, or any other material, it slows down. The amount that it slows down depends on the material and how energetic the wave is. The relationship between wavelength and frequency for a wave is described by a simple equation, v equals lambda f, where v is the velocity of the wave, lambda is the wavelength, and f is the frequency. This equation shows the inverse relationship between the wavelength and the frequency. This means that if one increases, the other must decrease. For example, gamma rays have the highest frequencies and the shortest wavelengths, while radio waves have the lowest frequencies and the longest wavelengths. The velocity of an electromagnetic wave is generally constant for a given medium that it is traveling through. The various wavelengths of electromagnetic radiation range from about 10 to the 8 meters down to 10 to the negative 16 meters. This is an incredibly enormous range. So what does the word electromagnetic mean anyway? Is it electric? Is it magnetic? All electromagnetic waves are composed of both electric and magnetic fields that oscillate at right angles to each other. These are also called transverse waves. In the 1800s, James Clerk Maxwell discovered that there is an important relationship between electric and magnetic fields. He developed his famous equations, aptly known as Maxwell's equations, that describe how moving electric fields create magnetic fields, and moving magnetic fields can create electric fields. Electromagnetic radiation, or waves, are created when electrically charged particles, like electrons, change their momentum. Now that we've gone over the electromagnetic spectrum and its properties, let's test your knowledge with a couple of questions. Number 1. Do all gamma rays have the same frequency? Do all microwaves have the same wavelength? A. Yes, all gamma radiation is the same frequency, and yes, all microwaves have the same wavelength. B. No, both frequency and wavelength can vary for each category of electromagnetic radiation. C. Yes, the gamma rays will have the same frequency, but the microwaves will vary in wavelength. Or D. No, the gamma rays will have different frequencies, but the microwaves will all have the same wavelength. The correct answer is B. Each category of electromagnetic radiation encompasses a range, and over that range, both the frequency and wavelength will vary. However, as the wavelength increases, the frequency must decrease. Number 2. Which type of radiation is most likely to be harmful to human tissues? A. X-rays, B. Radio waves, C. Infrared waves, or D. Green light. The correct answer is A. Only the very high energy types of radiation are able to penetrate and cause harm to human cells. Generally, these include gamma, X-ray, and ultraviolet radiation. Any of the lower energy types of radiation are not energetic enough to cause harm.
Light is a part of our everyday experience, and we cannot live without it. But what exactly is light and how does it work? In this video, we'll discover what light is and see what forms it takes as it interacts with the world around us. What is light? Although we don't generally think of light that we see every day as radiation, that is exactly what light is. Light can be considered electromagnetic radiation and encompasses many forms, including the visible light from light bulbs, the microwaves that cook our food, the X-rays used to make pictures of our insides, and the ultraviolet light that gives us sunburns. All of these are forms of light. All types of light act as a wave with a wavelength and a frequency. The wavelength of a light wave is considered to be the distance from crest to crest or trough to trough, where the trough is the lowest part of the wave and the crest is the highest. The frequency can be thought of as the number of oscillations per second or the number of crests or troughs that pass a certain point per second. In a vacuum, these waves all travel at the speed of light, c, which is roughly 300,000 kilometers per second, faster than anything else in the universe. However, when light is traveling through air, water, or any other materials, it slows down. The amount that it slows down depends on the material. The spectrum of light, as far as scientists can measure, continuously ranges from wavelengths of about 10 to the 8th meters down to 10 to the negative 16th meters, with the highest energy light having short wavelengths and high frequencies, and the lowest energy light having long wavelengths and low frequencies. This is an incredibly enormous range. The light we're able to see with our eyes is actually only a small range when compared to the entire spectrum. As you can see, the spectrum is categorized into several ranges, from gamma rays all the way to long radio waves. Visible light wavelengths range from about 380 to 760 nanometers, or 3.8 times 10 to the negative 7th meters to 7.6 times 10 to the negative 7th meters. The visible light spectrum is further divided by color, with red light at the long wavelength end and violet at the short wavelength end. We don't usually see color as individual wavelengths of light in our daily lives, except with special tools like lasers that can isolate a specific wavelength. Instead, we see combinations of wavelengths that our brains process as specific colors. The light from the sun is called white light, and it contains all of the wavelengths of visible light at approximately equal intensities. Light interacts with matter in various ways, usually depending on the wavelength, or frequency of the particular light wave, and also the composition of the material it's interacting with. When light hits matter, it may be reflected or refracted, or it may pass directly through unchanged. When light is reflected, it simply bounces off the reflecting material. When light is refracted, it bends and is then transmitted at a different angle. This generally describes the behavior of light of one wavelength. But what if white light hits a refracting surface? In this case, the varying wavelengths of the light beam cause refraction to happen at different angles for each color of light. This phenomenon is referred to as dispersion. If you've ever seen a light going through a prism, you've witnessed dispersion. Prisms, as well as other materials like glass, have light refracting properties. When white light hits the surface, the different colors of light separate because of their differing wavelengths. Shorter wavelengths, violet, get refracted more than the longer wavelengths, like red. They refract again once they leave the prism due to the differences in refractive properties between air and the prism. Light is an enigmatic thing in that it can be considered an electromagnetic wave or a particle called a photon. What we've talked about so far are ways that light behaves as a wave. Most waves, like sound waves or waves in water, must have a medium to travel through. But light does not require a medium and is able to travel and spread through a vacuum. This is where the particle properties of light begin to take effect. In a phenomenon called the photoelectric effect, it was noticed that light that was coming into contact with metal was able to knock electrons off the surface. In these experiments, light behaves as a particle because the electrons could only be knocked off or emitted when they received a certain amount of energy from the light. In the classical view of physics, the electrons should have been released after receiving that amount of energy from lower frequency light by storing it until it had enough energy to be emitted. That wasn't the case. The electrons were only emitted when the light they received passed a certain threshold of energy or a higher frequency. It seemed to Einstein that the atoms required specific packets of energy in order to emit electrons, which were termed photons. These days, it is generally accepted that light behaves as both waves and particles, and that quantum mechanics is to blame for this odd behavior. Now that we've discussed the properties of light, let's test our knowledge with a couple of questions. Number 1, looking at the electromagnetic spectrum, what is the second highest frequency type of electromagnetic radiation of the choices below? A, blue light, B, yellow light, C, X-rays, or D, AM radio waves? The correct answer is A, blue light. Of the options given, the frequencies in decreasing order would be X-rays, blue light, yellow light, and then AM radio waves. Number 2, will a prism separate ultraviolet light along with visible light? Would it be refracted more or less than visible light? A, yes, it will be separated and will be refracted more than all visible light. B, yes, it will be separated and will be refracted less than all visible light. C, no, a prism will only separate visible colors. The correct answer is A. Any type of light can be separated because they all have different wavelengths and frequencies, which will affect the refraction. Since UV light has a higher frequency, it will be refracted more than visible light. Magnetism is one area of physics that most people have first-hand experience with, since magnets are fairly common everyday objects. Today we'll be looking at different types of magnets and seeing just how magnetism works. So, what are magnets exactly? Simply put, magnets are materials that have a magnetic field. The magnetic field of a magnet is invisible, but it does have a visible effect when it repels or attracts other magnets in its presence. An example I'm sure you're familiar with is a refrigerator magnet. We know that both the magnet and the refrigerator door are magnetic and have a magnetic field because the magnet sticks to the refrigerator door. Every magnet has a north and south pole. The north pole of one magnet and the south pole of a different magnet will experience an attractive magnetic force when they are near each other, while the north to north and south to south poles experience a repulsive force when they are near each other. In order to describe magnetic fields, we draw magnetic field lines that come out of the north pole and reconnect to the magnet at the south pole. Magnetic field lines will never cross, and they will either loop back around to the opposite pole of the same magnet or connect to another nearby magnet. Technically, the field lines continue through the magnet, creating a closed loop. The denser these lines are, the stronger the magnetic field is in that spot. And as you might expect, if the magnetic field is strong, the magnetic force is strong as well. As a simple experiment, this concept can be visualized by sprinkling magnetic iron shavings around a magnet. The shavings will actually align themselves with the magnetic field. To make things even more interesting, you can add more magnets and see how the field lines change. It is important to note the relationship between magnetic fields and electric current. Moving charges create electric current. Anytime there is an electric current, there is also a magnetic field around it. The magnetic field disappears when the current is stopped. On a much smaller scale, magnets actually consist of many tiny magnets. The electrons naturally have their own magnetic fields because they are moving charges, even when bound in the orbitals around the atoms. For most materials, the electron orbitals are arranged such that all the tiny fields created by the electrons cancel each other out. This results in no magnetic properties. However, in some materials, the magnetic fields of the electrons are not all canceled out, which encourages neighboring atoms to line up with the field. If enough fields align, then all of those tiny magnetic fields add up to one big magnetic field, making the material magnetic. This state doesn't often occur naturally, but it can. In some materials, it is possible to align all of the tiny magnets and create a magnetic material. This occurs when the randomly oriented magnetic fields of electrons have the ability to change orientation. This property is referred to as ferromagnetism. Ferromagnetic materials are used to make artificial magnets like those on your refrigerator. Rare earth metals such as samarium and neodymium exhibit this kind of behavior. In order to magnetize a material, it must be submerged in a strong external magnetic field. The magnetic fields of the electrons in the material will then align themselves with the external field and remain that way. The ability of the ferromagnet to retain its magnetic ability depends on the material. Some artificial magnets are permanent, while others are only magnetic when they are exposed to another magnetic field. However, even permanent magnets will lose their imposed magnetic field at a certain high temperature, called the Curie temperature. Each type of magnetic material has a different Curie temperature. Magnets can also occur naturally, although naturally occurring magnets are generally weaker than artificial magnets. The strongest natural magnet on Earth is magnetite, an iron oxide also known as lodestone. A few other naturally occurring magnetic materials are hematite and pyrrhotite, which are both relatively weak magnets. Aside from minerals, the Earth itself actually has its own magnetic field, and although it is weak, it protects us by deflecting certain dangerous particles from our atmosphere. Although it is not intuitive, what we refer to as the North Pole is actually the South Pole of Earth's magnetic field, and the geographic south is the north end of the magnet. Now that we've learned all about magnets and how they work, let's test your knowledge with some review questions. Number 1. How would you draw the field lines coming out of the North Pole of magnet A if it was put right in the middle of the North Pole and south pole of magnets B and C. A, half of the lines coming from the magnet A would connect to the north pole of magnet B, and the other half would connect to the south pole of magnet C. B, the lines coming out of the north pole of magnet A would all avoid the north pole of magnet B as much as possible and connect with the south pole of magnet C. C, the magnetic field lines in each magnet would still come out of the north pole and only connect to its own south pole, so all the three magnet lines would just cross each other. The correct answer is B. Field lines will always go from the north pole to the closest south pole and will never cross each other. Number 2. Given the arrangement of magnets, which of the following would you expect to happen if the magnets are fixed at their midpoints but freely able to rotate? A, B, C. The correct answer is B. The magnets will rotate as little as possible, but will turn toward opposing poles.
Have you ever gone to open a door and received a painful shock from the metal doorknob? Maybe as a kid in school, you rubbed a balloon on your hair to make your hair stand up. These are both examples of static electricity in action. Today, we're going to talk about what static electricity is and where it comes from. Let's start by looking at what causes static electricity. Static electricity is caused by the tiny charged particles, called electrons and protons, that make up matter. These particles can be positively charged or negatively charged. Due to the electric force, protons and electrons are attracted to each other and will move toward each other if possible. On the other hand, electrons are repelled by other electrons, just as protons are repelled by other protons, and they'll move away from each other if possible. This attraction and repulsion can cause a large amount of charge to move from one material to another. The effects of static electricity occur when there is an imbalance of protons and electrons on a material. When there are an equal number of protons or electrons on an object, the object will be neutrally charged, but with excess electrons or protons, the object or surface will have a net positive or negative charge and exhibit static electricity. A great example of this is the balloon scenario I mentioned earlier. When a rubber balloon is rubbed on certain materials, like hair, it will pick up extra electrons. This makes the whole balloon negatively charged, since there are more electrons than protons on the balloon. The negative charge of the balloon will be attracted to materials or surfaces that have a net positive charge, or a neutral object whose electrons may move away. This is why you might see a balloon looking like it is stuck to a wall or some other object. Sometimes, if the loose electrons are unable to move to another charged object, they will gather at the end of the object that is near something with opposite charge. When this occurs, the object is said to be polarized, meaning that one end of the object is negatively charged and the other end is positively charged. This is similar to the polarized ends of a magnet. In most cases, static electricity is simply caused by two objects coming in contact with each other. Some types of materials have atoms with outer electron shells that are missing electrons, while others have loosely bound electrons on the surface. When these two types of materials come in contact with each other, they are easily charged. This is referred to as the triboelectric effect. More rarely, some materials may become charged with high heat or pressure. So, what causes the shock associated with static electricity? If there is a big enough imbalance in charges on an object, a static discharge may occur by some of the charge flowing to nearby surroundings suddenly. If the charge flows through particles in the air, it may cause a visible spark or even a painful shock. One very dramatic case of electrostatic discharge is lightning, where electric charges flow in clouds or from clouds to the ground. The effects of electrostatic discharge can be dangerous. Sparks or shocks to electronic devices may cause damage to the device, but they may also be harmful to us. If it is a small shock, it is not likely to cause us any real pain or damage, and may even be a fun experiment if it is in a well-controlled environment. On the other hand, if an electrostatic spark occurs near flammable or combustible substances like gas, it could possibly cause a fire. What can you do to reduce the risks? Luckily, it is quite easy to safely discharge static electricity by touching a conductive object, like metal or the ground. This allows the excess charge to flow away without causing a spark or sudden shock. This discharging is referred to as grounding. Now that we've learned all about how static electricity works, let's go over a couple of quick review questions. Number 1. If two balloons, each carrying a net negative static charge, are brought near each other, what will happen? A. They will be attracted to each other and stick together. B. Nothing will happen. They will not react to each other. C. They will explode. Or D. They will repel each other and move apart. The correct answer is D. Negative charges will repel other negative charges. This will force the balloons to move apart. Number 2. You have acquired a static charge on your body, but need to fill your gas tank. Which of the following would prevent causing a spark that could ignite the gas? A. Touching something metal. B. Rubbing your feet on some carpet. C. Rubbing your hair and sweater with a balloon. Or D. Talking on your phone. The correct answer is A. You'll need to ground yourself and discharge the static charge to prevent a spark.
Simple machines refers to the most basic set of tools that can be used to facilitate work. When we use a simple machine on an object, we're able to apply a force over a distance in order to achieve a greater force over a shorter distance. So the simple machine enables us to exert a force that we may not be able to exert otherwise. Before we get any further, let's remember that work is defined by a force multiplied by the distance over which the force is applied. So W equals F times D. Energy is always conserved. So when we put some amount of work into a simple machine, we're actually still getting that same amount of work out of the machine, assuming no energy is lost in friction. In other words, input work equals output work. Then we can substitute in F times D for the input and output work. Input force times D1 equals output force times D2. Input force is the force we apply to the machine. D1 is the distance over which we apply that force. Output force is the force the machine applies to the load we are moving, and D2 is the distance over which the machine applies the force. The important concept here is that, while the amount of work isn't changing, the force applied by us can be different from the force on the load, as long as the distances are different. From this idea, we get the concept of mechanical advantage, or MA. MA equals output force over input force equals D1 over D2. The mechanical advantage is a ratio that describes how much the machine amplifies the force you're putting into it. So MA greater than 1 is what we're looking for in a machine, which means the machine is increasing the force. Now let's look at some examples of these simple machines. There are considered to be 6 different types of simple machines: the lever, the pulley, the inclined plane, the wheel and axle, the wedge, and the screw. It may not be obvious how the input and output forces work in each of these machines, so let's take a closer look at each type. Lever. A lever is essentially any long board or rigid device with a pivot point or fulcrum. The object or load that you want to do work on is at one end of the lever, and you exert a force at the opposite end. The distances that each end moves up or down are D1 and D2. Inclined plane. An inclined plane is simply a ramp that can be used to move an object a certain vertical distance using less force than if you were to directly lift up. In the case of an inclined plane, the plane isn't necessarily moving anything itself, but it provides a means for you to push or pull an object to that vertical distance more easily. Here, input force and D1 are directed along the plane, while output force and D2 are along the vertical distance the object has moved. Wedge. A wedge is a simple machine that is often used to pry something apart or to cut it into 2 pieces. An axe is a great example of a wedge. The input force is directed downward into the crack. Think of how you apply the force on a knife when chopping food. And the distance is simply how far in you push the wedge. The output force is the force pushing the 2 pieces apart, and the distance is how far apart the 2 pieces have been displaced. Wheel and axle. A wheel and axle is a slightly more complicated type of lever, where the ratio of distance to the force that is applied is proportional to the radii of the wheel and the axle. For the mechanical advantage, we can use MA equals output force over input force equals the radius of the wheel over radius of the axle. The smaller input force is applied to the wheel, which has a larger radius and diameter, while the larger output force is exerted by the axle, which has a smaller radius and diameter. Pulleys. There are a few different types of pulleys, but all involve one or more wheels with a rope set in a groove along the diameter of the wheel. The load you're trying to move is attached to one end of the rope, while the input force is exerted, the rope is pulled, at the other end. For a simple one-wheeled pulley system, the magnitude of the input and output force are actually equal. However, the pulley system allows you to apply a force in a different direction to move the load. Think about a well with a pulley system at the top and a rope attached to a bucket of water. While you still have to exert a force equal to the weight of the bucket along an equal distance that the bucket has moved, the direction you're pulling the rope is likely different than the vertical motion of the bucket, thus making it easier to retrieve the bucket. Of course, this kind of system may not always be useful. And that's why many pulley systems are composed of more than one pulley, which allows the distances and forces to vary, therefore increasing the mechanical advantage. Here, you can see how the input force, F2, decreases as more pulleys are added to the system, while the load mass and force stay the same. Luckily, the mechanical advantage is simple to calculate for these systems. It is simply equal to the number of pulleys in the system. Screws. Screws are actually just inclined planes wrapping around a kind of cylinder. These include traditional screws used in woodwork, bottle caps, and various screws used in machinery. The forces and distances occur in a circular motion with screws, so the mechanical advantage looks a little different than with a regular inclined plane. However, every time a screw is turned 360 degrees, it penetrates the material by the width of the thread of the screw. This can be thought of as the distance associated with the output force, while the circumference of the screw can be thought of as the distance associated with the input force, since we must turn the screw by that amount to get the screw to go in by a thread width. So the mechanical advantage is MA equals output force over input force equals 2 pi r screw over the width of the thread. Now that we've gone over the physics behind simple machines, let's test your knowledge with some questions. Number 1. If you apply a force of 12 newtons to one end of a lever, and the resulting force on the object at the other end is 20 newtons, will the object move the same distance that you applied the 12 newtons of force? A. No, it will move a longer distance. B. No, it will move a shorter distance. C. Yes, it will be the same distance. Or D. There's no way to know without knowing the distance you moved it. The correct answer is B. If the force on the object is greater than the force you applied at the other end of the lever, then the distance the object moves will always be shorter. Number 2. How can you increase the mechanical advantage of a system of pulleys? A. Increase the length of the rope. B. Increase the mass of the load. C. Add additional pulleys to the system. Or D. You cannot increase the mechanical advantage. The correct answer is C. The mechanical advantage is equal to the number of pulleys.
Thermodynamics is a branch of physical science, or physics, that focuses on the correlation of heat and all other forms of energy, and consequently, all forms of energy that relate to one another. Well, the 4 laws of thermodynamics work to define the foundational physical quantities that mark thermodynamic processes when at thermal equilibrium. These foundational physical quantities include temperature, energy, and entropy. Now, let's take a look at how these laws are defined. The 0th law actually came after the first 3 laws of thermodynamics, but it was actually so fundamental and provided a basis for the other laws that it got the name 0th. That way, people knew the order in which they should learn or think through the other laws. So, what does the 0th law actually state? Let's take a look. Let's say that you have 2 systems, A and B, that are connected to each other with some sort of barrier between them. Well, the heat or energy of A will transfer over to B, or vice versa. The energy of B will transfer over to A. This is assuming that the wall is diathermic, meaning that heat can be exchanged, as opposed to an adiabatic wall, which would not allow for heat to pass. Once heat or energy is transferred between 2 systems such that there is no more heat being transferred or the transference of heat stops, then the systems have reached equilibrium, more specifically thermal equilibrium, since we are talking about heat. Now, let's say that we have another system, A and C, and they also reach equilibrium. Well, since A is in equilibrium with B and A is in equilibrium with C, then when you take B and C and place them together with a diathermic wall, then there will be no transference of heat. This is because the two systems are already at equilibrium together. To say this mathematically, you could say if A equals B and A equals C, then B is equal to C. That's the 0th law of thermodynamics. For some of you, this may seem like common sense. To others, it may seem counterintuitive, especially if you are super familiar with Boyle's law. Regardless, this is what the 0th law shows us, but it gives us much more than that. The illustration you just saw tells us something. What is that? What is that physical quantity which determines that the two systems will reach equilibrium and the transference of heat will stop from one system to the other? Well, it's this very physical quantity that was discovered later. There were already two laws of thermodynamics in place, the first law and the second law. Well, in these two laws, the term temperature was used, which was thought of as this degree of hotness, basically. While the term temperature was being used in the first and second law, no one could actually define it. There wasn't really a way to define temperature within thermodynamics. So, the 0th law was made so that temperature could be defined. So, how is temperature defined? Here we go. If there are two systems in contact with each other, then the direction of heat flow tells us that one body is at a higher temperature and the receiving body is at a lower temperature. So, temperature is the physical quantity which determines the flow or direction of heat. So temperature decides if heat will flow from A to B or from B to A. Let's review that real quick. First, 0th law says that if two systems, C and B, are in thermal equilibrium separately with a system A, then C and B are also in thermal equilibrium with each other. Secondly, the physical quantity defined in the 0th law is temperature. And lastly, temperature can be defined as the physical quantity which determines the direction of flow of heat and is the one that is equal in a state of equilibrium of two systems. That was the 0th law of thermodynamics. Now, let's take a look at the first law of thermodynamics. Here's what the first law of thermodynamics states. Heat energy given to a system is converted to its internal energy and work done on that system. To put this even simpler, the first law of thermodynamics just states that energy cannot be created or destroyed. It can only be transformed. Let's look at that mathematically. Internal energy represented by delta U is equal to heat energy plus work done. This equation is known as the first law of thermodynamics. But I'm guessing this still doesn't make sense to you. I don't blame you. Let's look at it this way. You have a system. Everything on the outside of that system is the surroundings. Well, energy can flow either into the system or out of the system. There are two ways in which energy can flow in and out of a system, which is through heat and work. So let's say that heat flows into the system. When heat flows into the system, then the system accumulates or gains energy. That energy is called the internal energy of the system, which is where we get our symbol U. The surroundings can do work on the system. So heat and work are the two ways in which a system can increase its internal energy. If the system's surroundings were to do 150 joules of work on the system, that means that the system's internal energy increases by 150 joules. And since the change is positive, delta U goes up. And since we know that energy cannot be created or destroyed, only transferred, the energy had to come from somewhere, the surroundings. So if the system's internal energy increases, then the energy of the surroundings must decrease. Well, energy follows this same principle. It cannot be created or destroyed, it's simply transformed or transferred from one place to another. The next law we will look at is the second law of thermodynamics. Now, the second law of thermodynamics might seem like an odd law. Why? Well, firstly, because the second law of thermodynamics doesn't tell us what can happen or what is possible. It only tells us what cannot be done or what is not possible. Another reason it might seem odd is because there are several ways to state it. The second law of thermodynamics states that the efficiency of a process can never be 1 or 100% of any machine. If a machine or process operated with 100% efficiency, then all of the heat or energy put into a system would be completely converted into work done, and there would be no heat rejected out. The second thing that the second law of thermodynamics states is that unless you apply a pump into a system, there is no way to send heat from a cooler source to a source at a higher temperature. Another popular way to state this law, as put by Clausius, is no process is possible whose sole result is the transfer of heat from a colder object to a hotter object. Put very simply, the second law of thermodynamics tells us that heat will never flow from a colder object to a hotter object unless you use a pump to do so. Like how a pump is used to cool the inside of a refrigerator. In every other case, however, heat always goes from the object at a higher temperature to the object with the lower temperature. And the other thing it states is that within a system or machine, heat or energy will never be 100% converted into work done. So if I put 100 joules into a system and I get more than 100 joules out of the system, then one of three things has happened. 1, I lied. 2, I miscalculated either my input or my output. Or 3, I just turned all of physics and science on its head and defied all of it. The third law and last law of thermodynamics defines absolute zero and brings together the concepts of entropy and temperature from the latter laws. The third law states that the entropy of a perfect crystal approaches zero at a temperature of absolute zero. We can't actually achieve absolute zero experimentally, or at least you probably won't. This is because we know from the second law that heat is spontaneously moving from a warmer body to a cooler body. So the object that you are trying to get to absolute zero will be constantly taking in heat from its surroundings. I said that the lowest possible entropy will only occur in a perfect crystal. Well, a perfect crystal is a structure where all of the atoms are identical and are positioned in perfectly symmetrical ways. If there are any imperfections in the crystal, then that imperfection carries an energy with it, which does not allow for the minimization of entropy. Another important note is that if we can't get to perfect zero, then there will never be complete stillness in our universe, because we will always have some sort of motion due to thermal energy.
Hi, and welcome to this review of Newton's first law of motion. In this video, we'll see how it forever changed people's perception of how and why things move. Understanding how and why things move has been the goal of scientists for thousands of years. Over time, calculations and experiments helped pave the way for a deeper understanding of motion, with Galileo Galilei defining the laws of gravity in the 1580s and Johannes Kepler penning his laws of planetary motion in 1618. The basis of our current understanding of motion comes from Sir Isaac Newton's 3 laws of motion, which he established in 1687. In this video, we'll be discussing his first law of motion, also known as the law of inertia. Newton's first law of motion states that an object at rest will stay at rest, and an object in motion will stay in motion unless acted on by a net external force. This statement is much more intuitive than it sounds. One of the key things to remember, though, is that this law is only valid for objects in an inertial reference frame. An inertial reference frame is a frame of reference that is moving at a constant velocity. Let's think of it this way. When you kick a soccer ball and it soars through the air, the soccer ball isn't the only thing that's moving. Remember, we're on a planet that's rotating at about 1,000 miles per hour, our solar system is moving at about 140 miles per second, and our galaxy is rotating at 130 miles per second. So objects that we consider to be stationary on Earth are technically moving at a speed of almost 1 million miles per hour. However, it's generally pointless to include the motion of things like the solar system and Earth when we talk about the motion of things on Earth, like cars or people. What we do instead is use Earth as a point of reference, or an inertial reference frame. That is, we discuss the motion of objects in reference to Earth. Let's take a look at an object in an inertial reference frame that has a velocity of 0. It would seem that there are no net external forces acting on the car since the car isn't moving. But what about gravity? Isn't that an external force? While it's true that gravity is pulling the car downward toward Earth, the car is on the ground, and the ground is providing a force in opposition to gravity. This force is called the normal force. Since you have two equal forces acting in opposite directions, the forces cancel out, meaning that the car does not move in the vertical direction. We define force by the symbol F, noting the force is a vector, which means it has both magnitude and direction. By doing this, we can state Newton's first law, mathematically, as the sum of the external forces is equal to the upward force of the ground on the car minus the downward force of gravity on the car, which is equal to 0. Note that the negative sign in front of the force of gravity indicates the downward direction of the force of gravity. This implies that the upward force is equal to the downward force. Now, let's imagine that someone comes along and pushes the car for a moment, providing an external force and giving it a small velocity. According to Newton's first law, once the external force is removed, the car should continue to move in a straight line with a constant speed for the rest of eternity unless some other external forces come along and change its speed or direction. Mathematically, we could state that the change in velocity with respect to time is 0. What we've just described is the constant motion of an object that is in a frame of reference with 0 velocity. However, what if we made the car the inertial frame of reference and discussed the motion of the passengers inside it? Imagine if you and I were sitting in that car and there were no other objects around. In that frame of reference, you and I are not moving with respect to each other. We are both moving in the same inertial frame. If the car changed speed or direction, you would feel it because your body wants to keep moving in the straight line with constant speed. If we look at the head as an object moving in the inertial frame of reference of the car, if the car sped up, your head would feel like it's being thrown backwards. This is because the part of your body that is attached to the car would speed up too, but your head wants to obey the law of inertia and continue moving at a constant velocity, that is, with the same speed and direction. Similarly, if the car were to turn to the left or the right, your head, due to inertia, would feel like it was being moved to the right or left. Let's look at another simple example in which you are trying to push a piano across the stage for your performance at your high school graduation. We have already discussed what the forces should be in the vertical direction, where gravity is pulling the piano down and the stage is pushing back up, so there is no net force in the vertical direction. In the horizontal direction, along the x-axis, we can add the pushing force and note that if the piano is not moving, there must be some other force pushing back against you. We can see that the resisting force of the piano is really the frictional force between the floor and the wheels of the piano and the friction in the wheel bearings. Since the piano has a constant speed of 0 and no direction, we can state Newton's first law as the sum of the forces is equal to the push force minus the force of the piano. This implies that the positive push force is equal to the negative pull force from the piano. Okay, let's wrap things up with a few review questions. Number 1, which of the following is the most accurate version of Newton's first law? The correct answer is C. Number 2, when you throw an object straight up, the object will slow down on its way up, stop for an instant, and then come back down with increasing speed in the opposite direction from its initial trajectory. Which of the following statements most accurately describes why this is the case? The correct answer is B. Number 3. Which of the following reasons describes why an object would not move when you push it? The correct answer is D. Hi, and welcome to this video on Newton's second law of motion. In this video, we will look at Newton's second law, compare it with his first law, and look at a couple of simple, common applications. Newton's second law states the acceleration of an object is directly proportional to the net external force applied, and it is indirectly proportional to its mass. In other words, more force generates more acceleration for a given mass, but more mass means less acceleration from a given force. Newton's second law is generally written in the form of F equals ma, where F is the net external force causing a mass, m, to undergo an acceleration, a. Since m is a positive quantity, the acceleration vector points in the same direction as the net external force vector. Newton's second law can be considered an extension of the first law for the situation where the sum of the net external forces is non-zero. As with Newton's first law, the internal forces are not included, and it can only be applied in an inertial frame of reference. Let's take a look at both a one-dimensional and a two-dimensional example to illustrate some applications of Newton's second law. Let's say you have someone pushing a piano across a stage. In this example, we are interested in the moment when the person pushes the piano with just enough force to get it moving. Let's set up the situation in which the first law holds, that is, the situation of translational equilibrium. The forces in the y direction, as we have seen, are the force of gravity downward and the force of the floor pushing up. In the x direction, we have the push force of the person in the positive x direction and the force of the piano pushing back in the negative x direction. When the person pushes with enough force to overcome the frictional forces resisting motion, the piano goes from a zero velocity to a non-zero velocity, and any change in velocity constitutes an acceleration. Thus, during the time when the velocity is changing, the net external force causes an acceleration, and Newton's second law comes into play. For the sake of completion, let's toss some numbers into our equation to get an idea of the numerical value of the acceleration. Let's say the frictional force between the wheels and the floor is 10 newtons, and the total friction in the bearings of the wheels is 10 newtons. Using Newton's first law for the x direction, we can calculate the net frictional force to determine the minimal force the person must push with. Newton's first law tells us that any pushing force greater than 20 newtons will get the piano moving. While the person may not have made the numerical calculation we did, they intuitively knew they had to push with a force greater than the number we calculated. So let's say they push with a force of 30 newtons and calculate the acceleration using Newton's second law, assuming the piano has a mass of 200 kilograms. Restating Newton's second law as the sum of the external forces in the x direction is equal to the push force minus the force of the piano pushing back, substituting in the values we discussed and solving for the acceleration yields a value of 0.05 meters per second squared for the acceleration. We just used Newton's second law to calculate the acceleration of the piano in one direction given the external forces. Now that we know the acceleration, assuming it is constant based on the constant external forces applied, we could use the equations of motion with constant acceleration to calculate the time of travel and final velocity given the initial velocity and initial and final positions. In fact, given those three equations of motion for constant acceleration, you can find any three unknowns given the other parameters. Let's take a look at a 2D example using Newton's second law. In this example, we will also use a static inertial frame of reference fixed on the origin of our mass. Imagine you're involved in a three-way tug-of-war. Each person is 120 degrees from the other, and the x-axis is lined up with one of the warriors. Imagine, initially, each person pulled with equal force, and there is no motion, so Newton's first law applies. We can use vector math to show the force components from each person in the x and y directions, starting with the person on the right. We can see all of their force is directed in the x direction, so the force in the y direction is 0. The force from person 2 has components in the x and y directions, as shown. Similarly, the force from person 3 must be broken down into its x and y components as shown. If we state Newton's laws for the three forces, we can see that Newton's first law holds. Let's say that the person aligned with the x-axis impulsively pulls with a force 1.3 times the force of the others. Using Newton's second law, we can calculate the acceleration of the center and the two people on the left. Let's assume that each person has the same mass of 50 kilograms and the rope has negligible mass. The mass of the system is then 150 kilograms. Now, let's say that F is equal to 100 newtons. Substituting those values into the force equation in the x direction and simplifying, we can calculate the acceleration. Intuitively, we know the direction of the acceleration is along the positive x-axis, and Newton's second law gives the quantitative value for the acceleration, which we calculated to be 0.2 meters per second squared. We just saw simple one-dimensional and two-dimensional applications of Newton's second law. When applying these principles to more complex examples, keep in mind that the concepts are the same, but the algebra may be a little more involved. Nonetheless, Newton's laws can be used to calculate the motion of all bodies in space, as long as they are moving in an inertial frame of reference. To wrap things up, let's go over a few review questions. Number 1. True or false? Unlike Newton's first law, Newton's second law is valid for bodies in motion in both inertial and non-inertial frames of reference. The correct answer is false. Both Newton's first and second laws are similar in that they account for motion in inertial reference frames. Number 2. True or false? Newton's second law is only valid for bodies with constant acceleration. The correct answer is false. Newton's second law can be used to find any acceleration. Number 3. Calculate the acceleration of the body in the diagram given the parameters indicated, assuming the mass is not lifted from the ground. Also calculate the force from the floor. Here's the correct calculation of the acceleration of the body, assuming the mass is not lifted from the ground. And here is the correct calculation of the force from the floor.
Hi, and welcome to this review of photosynthesis. Today we'll be looking at exactly how this process works and talk about why photosynthesis is so important to plants and animals alike. So what exactly is photosynthesis? It's the process of converting carbon dioxide from the atmosphere, water, and sunlight into glucose and oxygen. As I'm sure you probably know, photosynthesis is a process that occurs in plants. But did you know that it also occurs in some bacteria, protists, and algae? In eukaryotic cells, like plant cells, photosynthesis takes place in an organelle called a chloroplast that contains a light-absorbing pigment called chlorophyll. Bacteria and other prokaryotic cells don't have chloroplasts and instead perform photosynthesis in another way, such as using free-floating chlorophyll in the cytoplasm. For today, though, we're going to focus solely on photosynthesis in eukaryotic plant cells. The equation for photosynthesis looks like this. If this looks familiar, that's because it's the reverse reaction of cellular respiration in animals. This is no coincidence either. Plants will undergo photosynthesis to generate glucose as a food source for themselves. Through this process, plants remove large amounts of carbon dioxide from the atmosphere and produce oxygen as a byproduct, which many organisms require. And since animals cannot produce their own energy, they undergo the process of cellular respiration using glucose and oxygen to eventually produce a different form of energy known as ATP. Let's take a closer look and see what's happening on the cellular level. The primary site of photosynthesis occurs in the mesophyll, which are the cells within a middle layer of leaf tissue. Each mesophyll cell contains chloroplasts, which have unique structures within it, such as stacks of pancake-like structures called thylakoids. Each of those stacks of thylakoid membranes are called a granum, and are really small, about 0.3 micrometers in height. The grana are surrounded by a cytoplasm-filled space called the stroma. The stroma contains everything the chloroplast will need to undergo photosynthesis. We can divide photosynthesis into two parts: a light-dependent phase that occurs first, and a light-independent phase that occurs last. Light-dependent reactions require large sums of light energy to produce two compounds, ATP and NADPH, which are needed for the next step of photosynthesis. More specifically, light is absorbed by photosystems, or large complexes of proteins and pigments that help collect light energy and are located in the thylakoid membrane. Light is first absorbed in photosystem 2, or PS2, and energy is transferred to the reaction center, P680, where it then boosts an electron to a high energy level. PS2 gets electrons from the process of photolysis, where water is split into oxygen and proton, or H+ ions. As the high-energy electron travels down the electron transport chain towards the next photosystem, photosystem 1, or PS1, it is losing energy. Once the electron arrives at PS1 and more light energy is absorbed, the electron is boosted to a high energy level with the help of the reaction center, P700. The electron then travels along the electron transport chain, converting NADP+ to NADPH, which acts as their energy electron carrier. As electrons move down the chain, they generate a proton motive force, or a high concentration of protons, in the thylakoid lumen. These protons will eventually be used by the enzyme ATP synthase to generate ATP molecules for starch synthesis. Remember, the purpose of the light-dependent phase is to produce both ATP and NADPH. Let's talk about the second phase that is especially unique to photosynthesis. Phase 2 of photosynthesis takes place in the stroma and is called the light-independent reaction because, unlike phase 1, it doesn't directly require sunlight to occur. During this phase, also known as the Calvin cycle, the NADPH and ATP generated during the light-dependent reaction are used to make a 3-carbon sugar, glyceraldehyde 3-phosphate, or G3P, that can later be used to make glucose. During carbon fixation, a carbon dioxide molecule combines with ribulose 1,5-biphosphate, or RUBP, that is catalyzed with the enzyme Rubisco. RUBP splits into 2 molecules of 3-phosphoglyceric acid, or 3-PGA. From here, ATP and NADPH convert the 3-PGA molecules into G3P. Some G3P is converted into glucose, while other G3P molecules are recycled to regenerate the RUBP molecules we encountered at the beginning of the cycle. The glucose can act as that food source, or it can be stored as a polysaccharide like starch or cellulose for later use by the plant. There we go. That's the whole process of how plants use photosynthesis. Before we go, let's look at a review question. What specific kind of reaction occurs during the light-dependent stage of photosynthesis between water and NADP+? Is it A, ionic reaction, B, carbon fixation, C, covalent bonding, or D, redox reaction? The correct answer is D. 2 molecules of water are oxidized while 2 molecules of NADP+ are reduced in the presence of light to produce 2 protons, 2 molecules of NADPH, and oxygen. This is a redox reaction.
Hey guys, welcome to this Mometrix video on eukaryotic and prokaryotic cells. In this video, we'll take a look at what each are and how they are different. Eukaryotes. Eukaryotes can be defined as any organism that has a cell or cells that are complex. More specifically, they have a membrane-bound nucleus where all their genetic information is stored. The nucleus is not the only organelle contained within a eukaryotic cell membrane, but a membrane-bound nucleus is unique to eukaryotes. All of the eukaryotic cell's DNA is linear and is stored within the nucleus. Eukaryotes can contain several other membrane-bound organelles, like a Golgi apparatus, endoplasmic reticulum, mitochondrion, and so on. Eukaryotic cells are large cells, generally between 10 to 100 micrometers. Guess what? You're a eukaryote, and all the cells that make you up are eukaryotic. Some other examples of eukaryotes include protists, fungi, plants, and animals. Prokaryotic cells, on the other hand, are not quite as complex as eukaryotic cells. A prokaryote is a non-complex, single-celled organism that does not contain a nucleus, nor does it contain any membrane-bound organelles. It's important to note that eukaryotes can be unicellular as well, but a prokaryote will always be unicellular. All of a prokaryote's DNA is circular-shaped and floats freely within the cytoplasm of the cell. Prokaryotes are much smaller than eukaryotes. They range in size from 1 to 5 micrometers. Examples of prokaryotes include bacteria and archaea.
Hi, and welcome to this video on mitosis. The cell cycle is continuous and occurs so that cells can grow, regenerate, or repair themselves. Mitosis is one of the specific stages of the cell cycle where cells prepare to divide. In order to do this successfully, cells must evenly split their genetic material, or DNA, between each cell. Mitosis only occurs in somatic cells, meaning all the cells in your body except for sex cells. It's important to remember that before cells undergo mitosis, they replicate their genetic material so that each daughter cell has the same genetic material as the parent cell. Let's take a second to talk about chromosomes. Chromosomes are condensed strands of DNA. They're divided into two sister chromatids held together by their centromere. However, as we'll see next, DNA is only organized like this for certain parts of the mitotic process. So, to make this simpler, we divide mitosis into 4 phases that happen in the following order: prophase, metaphase, anaphase, and telophase, or PMAT if that helps you remember. Let's look at this a little closer. We start with a somatic cell, since that's the kind of cell that will undergo mitosis. Our cell is a human diploid cell, which means it has 2 sets of chromosomes, one set of 23 from our mother and one set of 23 from our father. This is true for all somatic cells in our body. Sometimes you'll see the shorthand for diploid as 2N. In order to maintain the number of chromosomes in our cells, the cell replicates its DNA before mitosis. So let's remember this as we look at the rest of the phases. During prophase, the cell's nuclear membrane dissolves and the chromosomes start to condense. Microtubules extending from the centrioles on both sides of the cell also begin to form. Together, they form a spindle apparatus called the centrosome that will eventually help move the chromosomes into place. Next, the cell will move into metaphase, where the microtubules attach to the centromeres of chromosomes, causing the chromosomes to line up along the equator of the cell. Now the cell is ready to enter anaphase. During this phase, chromosomes get pulled apart into their sister chromatids and move to opposite ends of the cell. The plasma membrane also starts to indent to prepare for the actual division of the cell. As a side note, we can now refer to these individual sister chromatids as independent chromosomes. Don't worry about this too much, but just be aware of the terminology here. Lastly, there's telophase. The chromosomes relax, the spindle apparatus disassembles, and the nuclear membrane reforms in each end of the cell. Lastly, the plasma membrane of the cell develops an even deeper furrow that will end up dividing the cell down the middle. The process where the cell actually divides itself in 2 is called cytokinesis. But this process stands by itself. Mitosis formally finishes up with telophase. Let's look at the end result a little closer. Remember how we started with a diploid cell with 46 total chromosomes? We've ended up with 2 diploid cells, also with 46 chromosomes total. These cells are called daughter cells and are identical to the one we started with. Before we go, let's look at a review question. During what phase of mitosis do the chromosomes line up along the equator of the cell? A. Prophase, B. Anaphase, C. Metaphase, or D. Telophase? The answer is C. Metaphase. All the microtubules attach to the centromeres of the chromosomes and pull them to the center of the cell so that we get an equal number of chromosomes when the cell undergoes cytokinesis. Thanks for watching and happy studying.